We had this very interesting workshop. I'm gonna talk about the Ginzburg-Landau distribution of some similarly exotic minimum models. And it's based on two papers with British Igor Andre with speaking in 30 minutes and Vladimir Laurov. So let me start with a very brief introduction of minimum models. In the famous EPZ paper, Galvin, Kulikov, and Anlochkov, they found an infinite family of exactly solvable 2D CFTs, which are nowadays known as the minimum models. These minimum models are specified by two co-prime integers P, Q. Once given P and Q, know the central charge, which is smaller than 1. And there is also a finite number of primaries. Here, HRS is the holomorphic dimension, and in our convention, phi r comma s is identified as phi p minus r comma q minus s. And the scaling dimension would be h plus h bar, and spin is h minus bar. And the mini models are unitary P equals Q plus minus 1. And in this case, then charge is just 1 minus 6 over Q. And charge, so essentially charge will be between 0 and 1. And the full spectrum is given by the ADE classification. In this talk, we are mainly talk about the A series and D series. A series means that you have diagonal modular variants. So you don't have a spinning field. And the OPE coefficients are given by the Donchenko-Padev formula. So basically we have all different formal data. But we don't fully understand the algebraic flows between different minimum models, and we don't have a pure theoretical description beyond the unitary minimum models. Like this theoretically, I mean vector space theory description. So let me review what we know in the unitary case.
Sorry. I thought that I was only for A series.
Yes, for A series, yeah. But that's good enough for us. Okay. The most famous Ginzburg-Landau distribution will be the 5-4 Lagrangian for the Ising minimum model M34, which is already in the DPD paper. And 3 years later, the model generalized to all the unitary minimum models. So unit M plus 1, M plus 2 is described by a scalar theory with a phi 2M potential. For example, the I think it's 3, 4, so M equals 2, you get phi 4, phi 4. I think is M equals 5, M equals 3, so you have a phi to 6. He also identified the primaries between the Ginzburg-Landau description and the minimum models. For example, here is an example of M67. So M equals 4. You get a phi to 8 potential. And for example, the phi 2, yeah, this is a label R. Here is the S. Phi 2 is identified as the Ginzburg-Landau field phi, and the phi 3 is phi squared. So, and the phi 4 is a phi to 8. And the phi to 9 is because it's phi to 10, right? So phi to 9 is a descendant by equation of motion, because d squared phi is the phi to 9. And here's some general pattern. Phi 2 is always identified as phi. So it works for any m. And the highest power here is identified as phi 1,3, because here is the phi 4, and but the symmetry, we know that phi 4 is same as 1,3. And these empty entries here, they are related to operators involving derivatives. I'm not gonna write them here. And in the okay, it's a different paper, but appearing at the same year. In the same year, the model found that there is an energy flow between two adjacent unitary minimum models triggered by the operator 513, which is which is the highest by and minus two operator. We can say. And he checked the flow by using conformal perturbation theory because he noticed that the 513 is a nearly marginal operator in the large M limit. So it deviates away from 2 by 1 or the 1 over M. And actually it's the only it's the only nearly marginal operator in this limit. So it just one conformal perturbation theory with only one operator. And this Ginzburg-Landau description provides a very intuitive way to understand the energy flow, right? Because in this model we have 5. On the right hand side we have 5 to 2M, and this term is more relevant. So in the other IR, this is the term that dominates. We can just drop the 5 to 2M, and we get n comma m plus 1. And okay, these are the unitary minimum models. What about the non-unitary cases? The simplest non-unitary model is M2,5, which has only one non-trivial primary, and it describes the Yang-Lee singularity. I'm not gonna go into the details because Ivan is giving a talk on Yang-Lee this afternoon. And the Landau-Ginzburg Lagrangian for Yang-Lee is a cubic, is given by a cubic potential with an imaginary coupling. So their G is imaginary. And the Ginzburg-Landau field phi is identified with the only non-trivial primary 512. And this theory has a PT symmetry that maps 512 to minus 512 and the I to minus I, which can be seen from the OBE. Here, it's not that by I don't mean that the OBE coefficient is exactly I. I just mean that the OBE coefficient is imaginary. So you see that this combination is invariant under this PT symmetry. And because of the operator identification, the GL description also have a PT symmetry that reflects the sign of phi and the maps I to minus I. And see, because the G is imaginary, right? So it becomes minus G on PT, and the phi cube becomes minus phi cube. So the potential is invariant under this PT.
But I'm not sure it doesn't require that there is no limit for ground state to be very negative. I want that, positivity of energy would be okay with type 2.
Again?
Imaginary couples.
Again?
No, imaginary couples, so it's still.
If it's real, it's not stable. The front end is negative, right? The ground end is negative, right? The lowest scalar dimension is negative.
Yeah, no, but okay, if we will take a normal quantum mechanics or whatever perspective, we would say the potential, was.
But because it's oscillating, it's not as bad as a real. If it's a real, it's really unstable. Yeah. And we can Yang-Lee can be understood from by turning on a imaginary magnetic field. And I think over here, we turn on this is the magnetic field, and M means we have above the critical temperature, and we can shift the phi field, get rid of the progress term, and then we can drop the phi term. We get it generates a phi cube term, and we can tune the magnetic field such that it's equal to the minus I to flow magnetic field, and then we get to the Yang-Lee action. But very little is known beyond the M25 minimum model. There are several proposals for M2Q, but I'm not gonna talk about it. Yeah. Okay, then the natural question is, can we construct Ginzburg-Landau descriptions for the other non-unitary minimum models? I'm not going to give a complete answer for this question, and I'm not sure. We're just to give some examples for V models beyond M25. First, there is a trivial example. The D series modular invariant of M3,10 is given by this action. As you can see, it's actually just the two decoupled copies of the Li because we have a phi 1q, phi 2q, and they don't interact, and they have the same coupling G. Oh. And this is due to a simple fact of many models that M25 hence M25 is the D series modular invariant of M310. And you can see this relation. For example, if we compute the central charge, M25 has central charge minus 22/5, and 310 has a central charge minus 44/5. So it's twice of the central charge of M25. And okay, for later convenience, we will define sigma as the sum of phi 1 and phi 2, and phi is the difference of phi 1 and phi 2. And we can rewrite the potential in terms of sigma and phi. Looks like a sigma q plus 3 sigma phi squared.
But the action looks like just sum of correction.
Yeah. I'll give that's just a trivial example, the starting point. You can identify the operators in the D series, which is the D series, the modular invariant position function. This is the D series modular invariant position function. And we have two copies of phi 1, phi. One has one is in the untwisted sector, and the other one comes from the twisted sector. And here are the scalar primaries. In this, the Z2 symmetry and the PP symmetry are derived from the OPEs. And on the Ginzburg-Landau side, we have a Z2 symmetry that swaps phi 1 and phi 2, which should be identified as the Z2 symmetry of the minimum model. So, for example, phi 1 plus phi 2 is the given, phi 1 minus phi 2 is Z2 odd. And in M25, each phi has a dimension minus 1. Has a holomorphic dimension minus 1/5. So here in 310 is also minus 1/5 because they decouple. So phi 1, phi 2 has dimension minus 2/5. Yes, yeah. And because there are crossing terms from the partition function, right? From 1,3 and 1,7, the crossing term gives the spin 1 field because it has dimension 3/5 and minus 2/5. And the spin 1 field should be identified as phi 1 d mu phi 1 d mu phi 2 minus phi 2 d mu phi 1 is also D2 even because this is also D2 odd because it comes from the twisted sector. And we also have a D2 primary, which is just the difference of the stress energy tensor, which is also D2 odd. Okay, it's just a trivial example. And but from study from the trivial example, we can flow to something non-trivial. It's found in this 2014 paper by Lin, Simon, John, Ido Gavnov, and Croatia Talakovsky. They found that in around the 6 dimensions, there is a perturbative flow starting from 310 model to another purely imaginary fixed point. More specifically, they studied this action. Now with general G2 and the G1 and the G2. There is a decoupled fixed point at the G1 equals G2, which corresponding to the Li or the M310 minimum model. But they found another fixed point here, G1, G2. So it's at this point it's an interacting theory. The two copies interact with each other. And here the blue point is the M310 minimum model, and you can see that there's a flow to another fixed point, IR fixed point. And the question is, what's the fixed point? What it describes? Is it some minimum model? And one thing we know that at that fixed point, because the couplings are still purely imaginary, it has a PT symmetry that gives a sign of sigma because sigma has the out powers and I minus I. It also has a Z2 symmetry that gives the sign of the minus phi. And we claim that in 2 dimensions, this fixed point describes the D series modular invariant of the M38 minimum model. Here I write down the partition function of the D series. And the first 2 terms, first 4 terms are from the untwisted sector, and the last 3 terms are from the twisted sector. Now I want to argue why this fixed point should be the M38 minimum model. The first evidence is the effective central charge theorem, which is a generalization of the Bloch-Fox C theorem for PT symmetric but non-unitary flows, which is proved in this paper. It claims that the effective central charge at the UV fixed point is larger than the effective central charge at the IR fixed point. And the effective central charge is defined as the usual central charge C minus 24 times the minimal holomorphic dimensions. So you see that for all the minimum models, the effective central charge is 1 minus 6 over PQ. And it's equal to the usual central charge for unitary minimum models, because in that case, the H minimal is just 0. But for non-unitary ones, the H minimal can be negative. Unlike central charge, the effective central charge for many models is always between 0 and 1. And for a non-unitary minimum model, the effective central charge captures the thermal free energy on a long cylinder. Here L is the length of the cylinder, log V is the free energy. And we'll consider theory with C bar effective equals C effective. So now we start with M310, and it has PQ equals 30. It should flows to something that with PQ less than 30. Here is a list of all these possible series. 4 times 7 is 28, smaller than 30. Okay. And the next evidence is the Z2 symmetry. And quickly review what the Z2 symmetry in many models. For many models with PQ both larger than 2, there is always a Z2 symmetry that's generated by the LQ minus 1,1 Berliner line. But the mini model M2Q does not have a Z2 symmetry. And in our case, M310, because both 3 and 10 are bigger than 2, there is a Z2 symmetry. And from the previous table, we know that 517 is a Z2 operator. So we expect that the IR series to have a Z2 symmetry. Then we can exclude all the M2Q minimum models in the previous list. All these candidates should be excluded. When the Z2 symmetry is non-anomalous, we can gauge the Z2 symmetry, and it maps the A series to D series and D series to A series. But the Z2 symmetry is not always non-anomalous. It's anomalous when both P and Q are odd. For example, if you can just write down the diagonal modular invariant of M35 and you try to opt for the Z2 symmetry. That's what you get from that procedure. You get complex coefficients in the after you do the gauging, which means that the signal is anomalous. So you getting that? Because we start with something that's where M310 does not, in M310, the Z2 is not anomalous. So with the 3.5 and the 3.7 should be excluded. And the third evidence is epsilon expansion. The renormalization of cubic scalar series are known to the 5-loop order. So we can using their results, we can compute the scaling dimensions of the operators in our series. For example, here is the scaling dimension of sigma to the epsilon to fifths. And we can do perturbative summation, for example, and we find like that sigma is around minus 0.49, and here by sigma square plus phi square, I mean a D to even quadratic operator. Because there are phi square and sigma square, there are two different linear combinations. One of them is a descendant by the equation of motion of sigma. Here I mean the other linear combination, that's a primary. And it has same dimension around 0.48. And these numbers are in favor of the 3.8 minimum model because the 5.13 has holomorphic different dimension minus 1/4, and so same dimension minus 1/2, and similarly 5.15 has a holomorphic dimension 1/4 and same dimension 1/2, which will end up these numbers are very close to these numbers. And here we have it's a how we identify all the scalar primaries. And the 5.17 it's a relevant operator that we can identify as the triggering cubic operator, and because the trigger static flow is expected to be irrelevant. And from the previous Cartesian function, there is also one string one operator with this same dimension, and we think it should be identified as sigma d mu phi and the phi d mu sigma. We compute the one same dimension is actually just 10% off. We hope to do higher relations with test that. So there are other evidence. For example, last year, Nakayama and Tanaka, they proposed an infinity family of RG flows. And based on non-invertible symmetry, the K equals 1 and I equals 1 flow is just a homological flow. And the K equals 1, I bigger than 1 flow, and the K equals 2 flows are started in the 90s. And our example is the first K equals 3 flow. And our invariant description is also consistent with the K equals 2 flow. You plug it with M38 can flow to M34 triggered by 5.15. Because 5.15 we just identified as a quadratic operator, so it gives a mass to the sigma field, and we can integrate out the sigma field, and if the massive field it gives a 5-4 potential, which is the IC model. And this flow can also be tested directly in using 2D Hamiltonian truncation. This also did in this paper. They did Hamiltonian truncation from 310, and then they also send on some irrelevant operators at M38, and the overlap region they can match. But unlike in the unitary case, the K bigger than 1 flows cannot be studied using conformal division theory, because the phi 1, 2K plus 1 it is indeed nearly marginal in the large Q limit, but the 3-point function behaves as 1 over Q. But for the conformal division theory to work, it should be of order 1. Okay, and that's the outlook. Currently, we want to know more GL descriptions for other mini models. I think Andre will talk about it. And we can also compute the sphere free energy, and to probe, and hopefully can match the central charge in 2D. I think Irina will talk about it on Friday. And also the more interesting one is recently Eric Eagle, Grisha, and Rand studied the Yanni model in various dimensions numerically using methods like body sphere regularization. and their results are in good quantitative agreement with the per-day extrapolations. It will be interesting to explore M38 in higher dimensions using similar numerical method. Given the operator identification, we can do two-sided per day for these for the operator dimensions. Here's an example for the sigma operator. We know the minus epsilon expansion around equals 6, and in 2D, we know the exact dimension should be -1/2, so we can do 3,3 per day, and it's actually a very linear line, and we get the numbers as equals 3, 4, 5. So when we do the sphere at 3D, we should expect to match that number 0.155, and then yes, that's for phi. This is for the quadratic even operator, and that's for the cubic even operator. And we can also try to identify the 2D quality primaries. Here are some proposals. The first one, okay, in the previous plot, we also see this combination, sigma q plus phi square sigma. But okay, they are two different linear combinations. The previous one should be identified as 517. Here, it's different from one. And we also have the per day for this D2 cubic operator by q plus by sigma square. And here we don't know the same dimension to epsilon to fixed. We only know it's to epsilon to cube, so we can only do 2 per day. Thank you.
Thank you for interesting talk. So we have a couple of minutes for questions. Yes.
I found that when you consider this kind of polynomial, that might, but genetically could be here like mu phi square multiplied by power of phi. It would not be connected with the model.
You mean in operator identification or in the action?
No, we started from mu phi square plus some polynomial and phi, right?
Yeah.
The model. Then I wonder about the case of the like mu phi square multiplied by some power of phi.
You can also think about that. That's more probably irrelevant in some cases, so it does not.
Because I'm thinking in terms of like the principal model, whatever, where you have Lagrangian like mu phi square multiplied by say divided by 1 plus phi square, right? It's a different type model, right? But here we have square, power, then you can redefine the but phi is equal to 5 dimensions, no? So field phi is in dimension. So for dimension, operator of the same dimension.
But for single field, you can redefine. It's redundant operator.
I see. So it could be in advance that we'll get back to mu phi square, right?
Yeah. Well, connected to me. So
That's the generalization of the electrical theorem. Is there some proposal in higher dimensions?
not about that.
Well, the context is because there's not a notion of qualified kineticity and qualified motion. Does that play a role in this prices at all?
Well, you have to guess quickly that the spectrum degree is right.
There's normally a notion that a new dark part form in space. So
Yeah, they use that. You probably remember.
oh,
All right. There are no more questions. Let's thank Zimo again.